Let's look at this circuit here. Terminal A and B, the switch before time equals 0, the switch is at this position, which means that this terminal have nothing there. There's no voltage here. But at time equals 0, the switch goes to this position. Then suddenly, at time equals 0, A and B have a voltage of V0 here now. So the same thing here. There's terminal A and B. Before time equals 0, the switch is at this position. There's no current flow through. But at time equals 0, the switch goes to this position. Therefore, suddenly at t equals 0, there is a current flow to the terminal A and B. So let's see how we describe these scenarios, two scenarios, mathematically. Describing them mathematically is very helpful to analyze circuits conveniently. Let's introduce unit step function. This function has a singularity at time equals 0, u of t, so that's a unit step function. This is a symbol. At t less than 0, that equals 0. At t greater than 0, that equals 1. At t equals 0, the value is not defined. So if we draw this function as here, when t less than 0, that's 0. When t greater than 0, that's 1. But at this exactly t equals 0, the function value is not defined. If the unit step function is shifted in time, therefore u of t minus t naught equals to 0 when t less than t naught and equals to 1 when t greater than t naught. So the graph will look like this. At t less than t naught, the value is 0. When t greater than t naught, the value is 1. So this is u of t minus t naught. This is 1, this is 0. So now we can see this circuit here can be expressed by terminal A and B, the same terminal here. And this function becomes V0 multiplied by u of t. So this is exactly describe this phenomena. Again, here for this terminal A and B here, so there's a current resource. The equivalent circuit is I0 multiplied by U of t. The terminal is the same, A and B. So these circuits, these two circuits are equivalent, and these two circuits are equivalent. Now let's look at step responses for RC circuit. So let's look at the circuit. At t less than 0, the switch is open. And at t equals 0, the switch suddenly closed. Therefore, there is a voltage source applied to the circuit now. Let's look at the transit. First of all, this circuit is the same as this circuit. These two are the same because this switch at t equals 0 closed is equivalent to the behavior of u of t. There is a voltage supply as Vs multiplied by u of t. The function Vs multiplied by u of t is expressed like this. So this is 0 time. At time greater than 0, Vs multiplied by u of t is Vs. And when t less than 0, that's 0. But the time exactly equals 0, the value is not defined. That's the time when the switch changed state. Now let's apply the KVL on the circuit. So the first element will be minus Vs u of t and plus, suppose the current is I in this direction. So I multiplied by R plus and V equals 0. Then use Ohm's law. Use Ohm's law for the capacitor. I equals to CT dv dt, and then plug it in, and then move this to the side here. So after we do that, this is the equation we obtain. That's this term r multiplied by I equal to c dv dt, and plus v, that's the voltage on the capacitor, and this term is on the side now. We can divide RC on both sides, and this is exactly the same equation as this one here. Now let's look at t greater than 0. So when t greater than 0, u of t equals to 1. Therefore, this equation becomes this equation. Now this is a first order equation, and we can solve v. Assume that at t equals 0, there's an initial voltage on the capacitor, v0. So which means that v of t equals 0 equals to v0, or v0 equals to v0. So these are the same notation. This is a v of t, complete picture here. At t less than 0, that's v0, that's initial voltage on the capacitor. But at t greater than 0, that's vs plus v0 minus vs multiplied by the e to the power minus t divided by tau, and tau equals to RC. Let's look at the plot of v0 with respect to time t here. So this is time t. At time less than 0, that's v0. The value is v0. At t greater than 0, there's some exponential function involved. We can see at t goes to infinity, then this whole term goes to 0. Before time goes to infinity, there's a transit time. So this is a transitional time here, which behave like exponential. So let's look at a circuit. At time less than 0, there is an initial voltage v0. At t greater than 0, vs multiplied u of t. This is a voltage supply that equals to vs now for t greater than 0. With time going, there's a charging period. It starts charging to the capacitor. As time goes to infinity, the full charge on the capacitor is equals to vs. So this is exactly this graph show. As time goes to infinity, the capacitor will fully charged to the voltage supply vs. Let's look at more insight of v of t when t greater than 0. When t greater than 0, the response can be decomposed as two portions. One portion is a natural response, is caused by v0, that's this term, v0 multiplied by e to the power minus t divided by tau. Because this is a natural response, it's due to the initial voltage only. The other portion is forced response, vs, this portion, and vs. Combine these two terms together, that will be this. So this is a forced response. So v of t composed of two portions. One is natural response, which is caused by the initial voltage. The second portion is caused by the independent voltage source vs there. We know that for natural responses, that's a source-free response. With time goes to infinity, this portion goes to 0. So this portion goes 0 when t goes to infinity. The other perspective to look at v of t is to divide v of t by transit response and steady response. In this case here, when t greater than 0, we always talk about when t greater than 0 because when t less than 0, that's v0, that's constant. Case when t greater than 0, this is actually t greater than 0. v of t equals two portions. One portion is transit response, the other one is steady state response. Then what is transit? response. The transit response is this portion. Eventually, this portion will go to 0 when time goes to infinity. So when time goes to infinity, v of t goes to 0. Let's look at a steadily response. Steadily response is the response when time goes to infinity. So in this case, it's equals to Vs. So this is the steadily response, and this portion is the transit response. And this is the V of t when t goes to infinity. Note that v0 equals to v at time equals 0, and vs that equals to v at time equals infinity. So this portion can be written in this formula now. So this is a general formula for step response of RC circuit. In summary, there are two perspectives. We can look at V of t when t greater than 0. The first one is to look at the cause of the response. We look at the natural response, which is caused by the initial voltage on the capacitor. The other portion is forced response, is caused by the independent voltage source. So this is one perspective to look at V of t. The other perspective is just to look at the behavior of time. One portion is a transit response. With the time goes to infinity, the value goes to 0. That's a transit. So transit response eventually disappear when the time goes to infinity. So the steadily response, that's the final value when the time goes to infinity. This perspective is more intuitive when we talk about V of t. So this is a formula we're going to use to calculate the step response for RC circuit. To calculate the step response of a RC circuit, we only need three components here. One is V infinity, which is the voltage at time goes to infinity. The second is the initial voltage on the capacitor, and the third is tau. So with these three parameters specified, we can obtain the step response of RC circuit.